Okay, so here's the output from the model I just ran. And a couple things to look at. First, at the top of the SAS output, you'll see some model information, a model information table. And note that they indicate that the response variable is CAD, coronary artery disease, and there are 2 levels. So that's good. You always want to double check that just to make sure. The sum of the frequencies used is actually your total sample size when you enter data using summary stats. So this is the total sample size is 78. And I'll say with summary stats. And good, that's what we counted up before, that there were 78 observations in our data set. And down here's a nice breakout of the total observations. There were 36 with no coronary disease, and there were 42 with coronary disease. That adds up to 78, so that's good. And then finally, you'll see probability model is CAD equals yes. Check this. Always check this so that you know what you're modeling, because if you forget to specify what level of event, or what the event level is that you want to model, then you might be a little confused as to what your results are telling you. The next thing in your output are some model fit statistics that we'll talk about later, but note here there's the AIC. You're familiar with the AIC from the multiple linear regression. We'll talk more about that. SC is actually just a short version for BIC. If you remember when I talked about that in chapter 6 notes, I mentioned that this is actually called Schwarz's Bayesian information criterion. So this is SC for Schwarz's criterion. We'll use the log likelihood here eventually. But notice, so we don't have an ANOVA table here, but we do have something here that says testing the global null hypothesis beta equals 0. That sounds familiar, doesn't it? Testing the global null hypothesis beta equals 0. This is actually going to take the place of our F test, and we'll talk more about that down below. We have some type 3 analysis effects. I mentioned type 3 sums of squares in passing in multiple linear regression, and that's what this table basically corresponds to. But now let's jump down here to the analysis of the maximum likelihood estimates. So again, this is your table of parameter estimates. From our population model on the previous page, we had a beta 0, a beta 1, and a beta 2 in our population model, if you recall. We had beta 0, the intercept. Beta 1 is attached to a dummy variable for males. Beta 2 is attached to a dummy variable for high ECG. And that's how I set this model up as well. So my estimate for beta 0 hat, is right here. My estimate for beta 1, which is attached to the dummy variable for males, is right here. And my estimate for beta 2, which is attached to the dummy variable for high ECG, is right here. Okay. And some other things to note is that we also get some, so the table of odds ratios will be of interest here. We get our estimated odds ratios for comparing males to females and high ECG to low ECG. And then we also, using the CL-PARM statement, this is CL-PARM equals WAD statement that we put in the model statement, we get our confidence limits for each of our betas in our model. So this is the output that you get from SAS. It's all nice and compact. So let's use this now. See if I can get this all on here. To write out the model equation with parameter estimates plugged in on the log odds scale, or the logit scale. So remember that logistic regression works on the logit scale. So the first thing it's going to estimate is on the logit scale. So we can say logit p hat of x, and I use the hat here because we're not actually modeling the probabilities, we're modeling the predicted probabilities from our observed data. And we can also say log p hat of x over 1 minus p hat of x, because remember logit just stands for log odds. And based on our estimated model here, this is going to be negative 1.1747 is our intercept, plus 1.277 times male. Remember, male is a dummy variable, which is 1 for males and 0 for females, plus 1.0545 times high for high ECGs. Okay, this is attached to ECGs greater than or equal to 0.1. This is ECGs less than 0.1. So our dummy variable again was for high. That's 1 for high ECGs and 0 for low ECGs. Do the results provide statistical evidence that sex and or ECGs are related to coronary artery disease? Write out the hypotheses, the test statistics, the p-values, and give brief interpretations. Well, let's look at, for sex, the null hypothesis. Remember that, so looking at our model parameters again, sex is attached to the beta 1 parameter. So the population parameter that we would want to test would be beta 1 is equal to 0, versus the alternative, beta 1 is not equal to 0. And hopefully this feels familiar to you from the linear regression. This is very similar. And the z statistic here is 1.277. Remember, it's the estimate minus the null value divided by the standard error of the estimate, 0.4854. I'm just writing this out to show you how this works. 2.564 would be our, if you do this calculation. But z squared is equal to the chi-squared in this case. So if we square 2.564, we get 6.575, which is exactly what we get for the chi-squared statistic here. So that's where that's coming from. It's just this divided by this squared, or the whole thing squared, and that's what you get. And the p-value associated with that is 0.0103. So what does that tell you? So that's evidence against the null hypothesis. We have sufficient evidence against the null and for the alternative. So it does look like sex is related to CAD. Let's go on with the next one now. Is ECG related to coronary artery disease? So now I'm going to test beta 2 is equal to 0 versus the alternative that beta 2 is not equal to 0. And again, beta 1 and beta 2 aren't fixed names for these parameters, but this is what I called it when I formulated the model. So I called the ECG parameter beta 2. So that's why I'm using that. So again here, I'm just going to jump right to z squared, which is the same as chi-squared, is 1.0545 divided by 0.4980. Subtract 0 in the numerator, but I won't write that out because it's 0. And if you do this calculation, you'll find it's 4.4844, which is the same as this chi-squared statistic up here. The p-value, it's hard to get this all on the screen at the same time. I apologize. The p-value is 0.0342. So I would say we have sufficient evidence that both sex and ECG are related to CAD. So these model results provide evidence that both sex and ECG are related to CAD. So now, this is a similar table that we looked at before. Let's complete the entries in this table using the model results. So we did this before at the population level, right? But now let's see what our estimates of those odds, log odds and odds are. So the estimated log odds now for females with a low ECG would just be, if we look at our model, females with a low ECG, males is 0, high is 0, so all we're left with is the intercept. So that's why I wrote the intercept down here. Females with a high ECG, we have the intercept. This is actually negative 1.1747 plus 1.0545 because we have a high ECG. So that's where I'm getting negative 0.1202. For males with a low ECG, it would be the intercept, beta 0 hat, plus, since we have males, beta 1 hat, but it's a low ECG, so we don't have high. So that'd be negative 1.1747 plus 1.277, which if you do that calculation is 0.1023. And finally, for males with a high ECG, we need all three terms. We have beta 0 hat plus beta 1 hat plus beta 2 hat, which is negative 1.1747 plus 1.277 plus 1.0545. So it's not looking good for males with a high ECG. And if you calculate that out, it's 1.1568. So the estimated odds of CAD for each of these, we can just exponentiate these values. So e to the minus 1.1747 is 0.3089. E to the negative 0.1202 is 0.8867. E to the 0.1023 is 1.1077. So I'm just exponentiating my log odds. And e to the 1.1568 is 3.1797. Okay. So now we're going to use the results above to confirm the odds ratios estimates in the SAS output. So the odds ratio estimates in the SAS output, we have odds ratios for comparing males to females, and also for comparing high ECG to low ECG. And remember that in this model, the odds ratio for males to females doesn't depend on ECG and vice versa. So let's first look at the odds ratio. If we look at sex, male versus female, we can compare males to females among those who have low ECG. So we would have male to female, I'm going to put 1.1077 over 0.3089. We could also look at the odds ratio comparing high ECG, or males to females among those who have high ECG, and you'll find that it's the same ratio according to this model, and that is an implicit assumption of this model, that the ratio stays the same. And you'll find that that's 3.586 if you do that calculation. And that's exactly what SAS told us it would be. Okay? Similarly, for ECG, I'm going to say greater than 0.1 versus less than 0.1. Again, we can look among either the males or among the females. So among the females, it was 0.8867 compared to 0.3089, which if we do that among the males, it would be 3.1797 over 1.1077. So this is among the females. Sorry. This is among the females, and this is among the males. Each of these ratios is going to be the same, and they're both going to be 2.871. Again, that corresponds to what SAS told us it would be. So let's continue on with this example. Verify the calculations for the 95% confidence interval for beta 1. Well, remember that the calculations for a confidence interval is going to be, this is a 95% confidence interval, so if you look back at my previous set of notes, that means we're going to use a z-score of 1.96. So my confidence interval will be beta 1 hat plus or minus 1.96 is the corresponding z-score, right? Z is equal to 1.96 if you look back at the table in my previous notes, times the standard error of beta 1 hat. And again, this is not a multiplication. This is a functional notation. So we can look back at our table here. Beta 1 hat is 1.277. Standard error 0.4980. So that'd be 1.277 plus or minus 1.96 times 0.4980 is the standard error. And if you calculate that out, 0.3009 to 2. So if we do the minus, it's 0.3009. If we do the plus, it's 2.2531. Okay. And lo and behold, 0.3009, 2.2530, so a little bit of rounding there. Okay. And then we can verify, so this verified the calculation for the 95% confidence interval for beta 1. Now we can verify the calculation for the 95% confidence interval for the odds ratio comparing males to females. Beta 1 is the parameter for comparing males to females. Okay. And to get the odds ratio, the confidence interval for the odds ratio, so to get the odds ratio, we can exponentiate beta 1. To get the confidence interval for the odds ratio, we can just exponentiate the confidence interval for beta 1. So our odds ratio, our 95% confidence interval for the odds ratio is e to the 0.3009 and e to the 2.2531. This is just refreshing your memory from something we talked about in the last set of notes. And if you do that, you'll get 1.351 to 9.517, which again, if we look back at our output, here's the odds ratio estimates. So if I take e to the beta 1, I'll get 3.586. Right? I think we showed that on the previous page here. Getting all turned around here. Yeah, e to 3.586. And if I take e to my confidence limits to each of the limits for the beta, I'll get 1.351 to 9.516, which is basically what I got. It's subject to some rounding here, but it's basically what I got when I did it myself. Now, interpret the confidence interval, 95% confidence interval for the odds ratio comparing males to females. So I would say we are 95% confident that the true odds of CAD for males is between 1.351 and 9.517 times the odds for females. which if you know anything about CAD, unfortunately this rings true. CAD is much more common in males than in females, coronary artery disease. And our data say, our model says it's between 1.35 times and 9.517 times the odds of CAD for females. I should say the odds of CAD for females. And I just have it as an exercise that you can try on your own. You should be able to do the above calculations for ECG. So we just did the odds ratio and the confidence interval and everything for males versus females. But now you should also be able to do the same calculations that we just did for high ECG versus low ECG. So I'd like you to try that as an exercise. And I'm going to pause this.